Good morning, everybody. So, to kind of recapitulate what we have already studied, we are discussing about isoparametric elements, and we have started with one-dimensional isoparametric elements, where you take a two-noded linear elements between points x1 and x2, physical coordinate points x1 and x2, and you map this particular element onto a an element in the natural coordinate system, which is specifically lying between u1 equal to -1 and u2 equal to +1, which means x1 maps onto u1, which is -1, x2, irrespective of the length distance between x1 and x2, maps onto u2, which is equal to 1. So any point between x1 and x2 will map onto some point between u1 and u2. I have given you the shape functions, and for isoparametric elements, the shape functions are also the mapping functions, which means that x is equal to n1 x1 plus n2 x2. At the same time, phi is equal to n1 phi1 plus n2 phi2. Now, if we are going to use these isoparametric elements, it means that the stiffness matrix, so once you take the residual, you apply the weak formulation, you obtain the term which is responsible for the stiffness matrix, which is one order less. You see that you have dn dx, whereas n is defined only in terms of u. So you will have to perform this integration where dn dx is equal to dn du into du dx, which gives us the relation between dn dx and dn du. dn dx and dn du are related by the Jacobian matrix, where the Jacobian J is equal to dx du, which can also be written in matrix form as d du xu, which we don't really have to bother at the moment, but which will become important as we go ahead. So if that is the case, then what we can do is we can evaluate each of these terms, dn dx, d phi dx, and n into phi in terms of n as a function of u. And this is the stiffness matrix that we get. We must remember to include dx as j du. So dx is not du, but dx is equal to j du from this expression. So that has to be put in the integration. And the integration points have changed. The integration bounds have changed from -1 to +1. So obviously, this is the advantage that we reap, that we can now perform an integration between two fixed points, -1 and +1. And this gives us an advantage in terms of being able to use numerical integration techniques rather than manual techniques, analytical techniques. So as you can see, if you want to convert the stiffness matrix in terms of the natural coordinate system u instead of the x, there are quite a bit more computation involved. You have to do mapping, you have to have chain rules performed for integration, etc. So there should be an advantage which kind of makes it meaningful to go to so much trouble. The advantages become obvious when the analytical integration is cumbersome or impossible. You may have irregular shapes, you may have complicated geometries, and it is not always necessary that your elements should be straight lines or regular domains. And when your differential equations become very complex and you are left with, as you had seen when I was working with the Laplace's equation, the stiffness matrix that you needed to calculate came out in terms of the coordinates, but that may not happen all the time. You may have complicated terms depending upon the equation. You may have complicated terms which you need to integrate to obtain the stiffness matrix. So what we would like to do is we would like to use numerical integration techniques, and this mapping from the x domain to the u domain makes it possible for us to use numerical techniques. And we will use a particular kind of numerical integration technique, and it will become very obvious why we choose that. So in the last class, I talked about various numerical techniques. I mean, you talked about it. I asked you and you said that you were familiar with various numerical integration techniques like one-third Simpson rule or trapezoidal method, etc. What we are going to use is a similar method, but a bit different. The basic idea is of course the same, and that is the Gauss Quadrature technique is what we are going to use. Now, as you know, in numerical integration, the integration is replaced by a summation. So any integration of a function fx over a domain a to b, integration fx dx will be evaluated in numerical methods as a limit of summation fxi dxi, I going from 1 to capital N, where n tends to infinity. What do I mean by that? Okay, this should be capital N. So look at this curve. This curve is what I want to integrate from, let's say x equal to a to x equal to b. So essentially what I need to do is I need to find the area under this curve. And I can imagine that this area is comprised of, blocks of area. So if I divide this area into small elements and I add the areas of all these elements, I'll get the total area. And that is the idea. So what I do is at any point xi, I take a rectangle which has width dxi, and then if I therefore multiply f at xi, so let's say this is f at xi, let's say this is xi, f at xi, I take the value and I multiply that value into dxi, I will get the area of this rectangle. And I can keep doing this for all i's possible. So I do it for many i's and I sum over all the i's. Now there is a problem here, as you can see. The area that I need to take is this area. So when I take fxi into dxi, I am actually ignoring this area. So I keep on doing it for every case, and over every case there will be some error. And I would not like that. Or at least I would like to minimize that error as much as possible. And I figure out a way of doing this. Let us see what we are trying to do. So essentially what we are trying, okay, and the other thing is this error will be minimum if I take a very large number of x's. So if my n tends to infinity, so if I have infinite such areas, then the error in each case will be very small, and that will make my accuracy as high as possible. So essentially, I would like to work with limits n tending to infinity, but that's not going to be possible because we will have to take a discrete number of points. So what I do is, see, this is equal to, and now I am approximating it. If it were infinity, I would get the exact value. I am not going to get an exact value with numerical integration techniques. I already accept that. I would just like to make it as accurate as possible. Now, what am I actually doing here? I am taking a sum over these areas. And which are these areas? These areas are obtained by multiplying the value of the function at any point xi and multiplying this by, let's say, a value, which could be, let's say, this is the thickness here, a very small thickness about xi, or some value which changes with xi. Let me call it w, the weighting function. So essentially, you can think that this value of f at any point is being weighted by the thickness, width of the, fxi is being weighted by the width of the block that you take. Let me call that wi. And then what I will say is that I know that I would like to take infinite number of points, but I know I cannot. I know that n has to be a finite number. And let me say that m is the number of integration points. That is, m is the number of xi's that you choose. So you take m number of points. And at each, for each integration point, xi is the integration point or the sampling point. And at every sampling point, you have a weighting coefficient wi. In this case, it is like the width of the rectangular strip whose height is given by fxi. But I'm not going to bother myself by the physical relevance of Wi. It may be the thickness, but what I am going to remember is that every fxi, so at every xi, I'm going to sample the function fxi, and every fxi has to be multiplied by a weighting coefficient. I am going to give you a technique for choosing the weighting coefficient. I'm also going to give you a technique for choosing the number of integration points. I have to choose a finite number. I cannot go with an infinite number. So what finite number do I choose? Do I choose it arbitrarily, or is there any rationale behind the choice? That is what I'm going to tell you in the next slide. Is it clear so far?
Ma'am.
Okay, so as you see, we have already normalized the integration domain. We are no longer going to obtain the integration between points x1 and x2. We are going to perform the integration between points -1 and +1. So we have already defined the domain between -1 and +1. Now I'm going to give you the statements of the Gauss-Legendre quadrature technique that we are going to use. What does Gauss-Legendre quadrature tells us? A polynomial function of order 2n minus 1 can be exactly integrated using an endpoint quadrature. This word is very important. We understand that whenever you are using a numerical technique, you are allowing some approximation. But in certain cases, it may be that the approximate value is equal to the exact value. That means there is error is 0. It is possible to make the error 0. And that is what we are trying to do. What we are saying is that if you have a polynomial function of order 2n minus 1, and if you use an endpoint quadrature, what is an endpoint quadrature? I'll come to later. But endpoint quadrature means there are n number of integration points or sampling points. If you use an endpoint quadrature, the integral value that you will obtain will be the exact value. There will be no error. So let us see what that means. For example, let's take a polynomial x squared plus x plus 1. Okay. So what point quadrature should you use to get an exact integral value? Ganesh? Look at the statement and give me the answer.
Ma'am, minimum 2.
How did you get that? So
2n minus 1 equal to 2.
Okay.
N equal to 3 by 2.
Yeah, n equal to 3 by 2. So you have to use at least 3 by 2. You cannot use 3 by 2 because you have to use an integral value. So you have to use 2, correct. So if you have a second order polynomial, you have to use a 2-point quadrature. If you have a linear polynomial, you can get away with a 1-point quadrature. So this tells me that given the polynomial, you can get the exact value using an endpoint quadrature. I also define here something called the degree of precision of a quadrature rule. The degree of precision of a quadrature rule is the degree of the highest order polynomial that can be exactly integrated. Which means that if you use 2-point quadrature, you can, of course, as we have just now seen, we can exactly integrate a second order polynomial. But if you take a third order polynomial, 2n minus 1 is equal to, let's say, 3. In that case also, you need a 2-point quadrature. But if you go above 3, 2-point quadrature is no longer possible. So the highest order of the polynomial which can be exactly integrated with a 2-point quadrature is 3. So therefore, degree of precision of second order Gauss rule is 3. So there are two ways of looking at it. If you have a 2n minus 1 polynomial function, then you must use an n-point quadrature. And if you use an n-point quadrature, then the degree of precision is given by the highest order polynomial that can be exactly integrated. So in this case, it is 3. Okay, I'll come to this later, this multidimensional thing later. So what does it exactly mean? Let's take an example. Let's say you are going to integrate. Let's take the same. Remember, the integration is always from -1 to +1. Now, this is something that you can integrate. So you can integrate and find the value, the exact value, and then you can validate. Now, what you have is, this is your Gauss's table. This is the table of, as you can see, let me see, axis and weight coefficients of the Gaussian quadrature formula. Integration -1 to 1 fx dx is equal to summation I equal to 1 to n hi fa. These are my sampling points and these are my weight functions. Whatever I have said w are given as 8. So as we have seen, if it is a second order polynomial and you want to integrate it exactly, you need a 2-point quadrature. So can you, by looking at this table, apply the 2-point quadrature and give me the value of this integration? So essentially your FA is A squared plus A plus 1. And you need to find FAI at n equal to 2. That means 2 points. So as you can see here, n equal to 2 plus minus A. So your sampling points are plus minus 1 by root 3. And the weights are 1. Which means you have to find f at 1 by root 3, multiply by 1, plus f at minus 1 by root 3 into 1, and that should be your so find it.
By 3. By 3.
Is it correct? Whatever I have done, is it correct? And second question is, does it match with the exact solution? Because this is something that you can find. So I'll leave you to do that. Let us take another case. Let us take n equal to 3. When you have n equal to 3, you have these points. So you will have to find f at 1 by, sorry. Into 5 by 9 plus f at minus 0.6 into 5 by 9 plus f at 0 into 8 by 9. So you have to make sure that you are taking the correct weights. Of course, this is plus minus 1, plus minus 0 does not make any difference. So it's just 3 points. So by using this Gauss quadrature rule, even though you are using a numerical integration technique, you would be able to obtain an exact integral. However, remember, You don't actually know fx. Okay, that is something I'll come to. So whatever you have, you can evaluate it exactly if you use the Gauss Quadrature rule, and that is why we use the Gauss Quadrature rule. So now I come back to this. Sorry. So if you look at this, if you have an integration, a multivariate integration. So far we have only been considering fx dx, or let's say fu du. Now I want to perform an integration because we will be using two-dimensional elements. I want to perform an integration over the domain u and v. So essentially I want to perform the integration fuv du dv -1 to +1, -1 to +1. So I can first concentrate on the internal integration, which is summation over I equal to 1 to n1, n1 being the number of integration points in the u direction. wi, wj, f, ui, vj, and then this has to be summed over j equal to 1 to n, n2, where n2 is the number of integration points in the v direction. And by doing this double summation, I should be able to find my double integration. So let us take an example. Can we do this? So what point quadrature should I need? Let's change this a little. Or for the first time, let us consider this original thing only. Yeah. Let's go with this. What point quadrature should I use? Teja?
Yes, ma'am.
What point quadrature should I use? Two? 2 in U and 2 in V. So how many points will you have? How many total integration points will you have?
4.
4. Perfect. So you will have, so what will be your integration points? This is 2. So f at 1 by root 3, 1 by root 3, into 1 plus f into minus 1 by root 3 into 1 by root 3 into 1 plus f of 1 by root 3 minus 1 by root 3 into 1 plus f minus 1 by root 3 minus 1 by root 3 into 1, right? This will give you the total integration. Is this clear to everybody? In that case, suppose we were working with this then. What do we do now? How many points do we have?
Total 3. 2, 1.
Into what?
Into 5 by 9. 5 by 9.
I didn't know,
Alright.
Baba.
Okay. 1 man.
1? Why not 2? See, you have got 1 by root 3, which is your u, and v is equal to 0.
Okay.
So 1 into 2.
1 into.
Wi into wj. Huh.
Okay.
Yeah. So f 1 minus root 3 into 0.
1 into.
Yeah. So did you get 3 points? Somebody say 3 points, right? It's 2 points really. Because u is minus root 3 and 1 root 3, and v is only 0. So you have 2 points.
Oh.
Is this clear to everybody?
Yes, ma'am.
Oh. Okay, one more thing is this. When you perform the integration, do not forget that you have the function. So if you have x, y, z, you can have u, v, p. So it will be a triple integration. Du, dv, dp. Do not forget the det j. So when you're performing the integration and you're mapping from xyz to uv, there will also be det j. And so when you are integrating over the xyz domain, and instead of doing that, when you are integrating over the uvw domain, do not forget the det j into du, dv, dp. That will be there in the picture. So you will actually have to integrate. You will actually have to integrate this whole thing. So not fxyz, but your f will be fuvp, det j will be the term inside your Gauss quadrature, which has to be evaluated in the new domain. And that can be done in the domain -1 to +1, -1 to +1. Is this clear to everybody?
Yes, ma'am.
I will quickly go over the 3 noded. So what we have been doing so far is we have been using only 1-dimensional element. We have just now started talking about 2-dimensional elements. So let us take a simple case of the simplest isoparametric element, which is the 3 noded triangular element. Because I want to point out something. The first thing is that look at the extent of your isoparametric triangular element. It does not go from -1 to +1 because, of course, it's a triangular element. So what you have here is the isoparametric element in case of a triangular element is enclosed by these 3 points, u is equal to 0, u is equal to 1, and v equal to 1. So this is your 0, 0. This is your 1, 0. And this is your 0, 1. So these are the 3 points. So shape functions of linear triangular elements in the natural coordinate system is defined as, again, I am giving you the elements, I am giving you the shape functions for the moment. That is going to change later, but for the moment, you just take what I give you. So the shape function is defined as u greater than equal to 0, v greater than equal to 0, and u plus v is less than equal to 1. Based on this, I give you the shape functions, N1. I do not explain how I give you these shape functions at the moment. N1 is equal to 1 minus u minus v. N2 is equal to u, N3 is equal to v. So N is a function of uv, N2 is a function of uv. So I am now in the domain N1 as N1, N2, N3 are functions of uv. Now we also know that what we are going to do is, we are going to use these shape functions as my mapping functions, which means x uv, x will now become a function of uv. X is my coordinate system, so it can be any triangle, any arbitrarily shaped triangle with points x1, y1. x3, y3. If you consider the x's only, n1 x is n1 x1 plus n2 x2 plus n3 x3, right? Similarly, y is n1 y1 plus n2 y2 plus n3 y3. Apart from that, your phi will also be equal to n1 phi1 plus n2 phi2 plus n3 phi3. All n's are functions of u and v, right? So x now becomes a function of u and v, y becomes a function of u and v, phi becomes a function of u and v, right? Everybody clear up to this point? Now, what I'm going to show you now is, I'm going to take the Poisson's equation and try to evaluate the stiffness matrix using these isoparametric shape functions. I'm not going to go through every step. This is the term that we need to evaluate, because I am here considering only the volume integral, because I'm interested in evaluating the stiffness matrix. You can always, if you know how to evaluate the stiffness matrix, you can always evaluate the other force vector or whatever you have. So as you can see here, we now have a relation between dn du, del n del u and del n del x. Also a relation between del n del v and del n del y. So del n del u is del x del u, del x del v, del y del u, del x del v, del n del x. What is this? This is the Jacobian matrix, right? Earlier we just had del x del u, which we call the Jacobian. Now we have x and y, so you have v and v, u and v as well. So this is your Jacobian matrix, which is 2 into 2. So therefore, differential of n or grad n can be written as j inverse del n del u and del n del v. Remember, we know n as functions of u and v, so we can evaluate these right-hand sides. And once we evaluate the right-hand sides, we can evaluate the differentiation of the shape functions or mapping functions in terms of x and y as well. So now we need to evaluate j. So if you have to evaluate, so as you have seen in the previous slide, I need to evaluate grad n. And if I need to evaluate grad n, I also need to, just like in the one-dimensional case, I need to evaluate j inverse. So let me try and find j. J used to be del del u of x. Now in 2 dimensions, j is del del u into del del v into x into y. X and y, where x is a function of uv, y is a function of uv. Again, n is written as how? n1 into x1, y1 plus n2 into x1, y2 plus n3 into x3, y3. So I am writing everything in terms of matrices. So I have del del u, del del b, n1, n2, n3. This is your shape function matrix, and this is your coordinate matrix. So what you have is the coordinates of the 3 points of the triangle, x1, y1, x2, y2, and x3, y3. Is this clear to everybody? This is just algebraic manipulation. We are doing exactly what we did for one dimension. So having done that, we also need to evaluate, we have evaluated grad n. We now need to evaluate grad phi. Epsilon I have taken out because we are considering epsilon to be isotropic and and homogeneous. So it's a scalar quantity and it's constant for a particular element. So phi is again n1 phi 1 plus n2 phi 2. So phi can be written as the shape function matrix multiplied by the nodal vector. So grad phi would be grad n phi I. Grad n I have already obtained. So I can now go ahead and evaluate this quantity. Now, what I need to evaluate is this quantity, grad phi dot grad ni. I'm ignoring epsilon. Grad phi dot grad ni. This is what I need to evaluate. Now, in order to do that, again, I want to do some manipulation. If I have two matrices A dot B, that can be written as B transpose A. So therefore, epsilon, if you consider this to be the A matrix and this to be the B matrix, A dot B has to be evaluated as grad n transpose epsilon grad phi. So therefore, this integration becomes grad n transpose epsilon grad phi dy dx when the integration is over x and y. Now, if I go from the xy domain to the dv domain, uv domain, I should not forget det j, which I keep on telling you. Phi remains as before. Grad n becomes j inverse grad n transpose, and this becomes, I've taken epsilon out, j inverse grad n and phi. Now phi can go out as before because phi is a constant quantity. Phi 1, phi 2, phi 3 are known or unknown constants. So the integral is only this quantity to be integrated over dv du domain. Epsilon I have taken out because it is uniform. What are my bounds? My bounds are 0 to 1 and 0 to 1 minus u. So now you know what is the function in u and v which has to be integrated in the domain u and v.
Ma'am, in 5 more minutes you have to finish.
Okay, I'll do that. So your FUV is this entire thing, which is not a problem. You can figure out what degree it is, what order it is, and you can choose your endpoint Gauss quadrature. But do you see a problem somewhere? Whatever. Do you see a problem here? If I give you this expression, can you go ahead and do the Gauss quadrature?
U is not specified.
Yes, firstly you have a u. Also the integration bounds are 0 to 1.
Yes, minus.
So you know how to do it from -1 to +1, -1 to +1. You do not know how to do it from 0 to 1. So the table that I have given you is not going to be useful at all. So what you have to do is, I will discuss this in the next class, but what you will need to do is you will need a separate table. You will need a different table. This is your Gauss integration table for the numerical integration formula for triangles. And that is not that straightforward because as you can see, there are 3 triangular points. I will come back to this later. So whatever discussion we have had in terms of the triangular elements, I have told you what needs to be integrated, but about the integration, I will come back later, not even in the next class. In the next class, I will discuss a little more about the integration, about the obtaining of the stiffness matrix, and I will go on to 4-noded quadrilateral elements. And then afterwards, I will come back to the integration in the numerical elements. But what you must remember is that you cannot use the table that I had just given you. This table that I had given you, you cannot use for integration over linear triangular elements because the bounds are completely different. So I'm also going to give you a different table, but you will also have to know how to use that table, which we will discuss in a later class. So if you don't have any questions, I'll stop a little early today. I have to conduct a defense. So. Balaji, I will give you the notes for the previous classes. Please remind me, you can put them up to whatever we have covered before isoparametric. I will give you the notes, the running notes, so the students can look at that. Okay, we'll meet tomorrow. And before we discuss tomorrow, if you have any questions, please ask, because as we go forward, if things remain unexplained, it is going to be difficult for you to understand. Okay, thank you.